Hey guys, welcome to our last video on forces. This is our last video before our test. This is all about Newton's third law. Before I jump in and tell you what Newton's third law is and spoil the fun, I'm going to lead up to it by talking about a new type of problem. The new type of problem we're going to look at is what happens when there are two objects that are experiencing forces together. These are referred to as two-body problems. Whenever you have a force problem with two objects that are touching, you're going to have to draw three free body diagrams, and I'll walk you through each one. But first, I want to clarify what I mean by touching. Touching doesn't mean that the objects, it can mean that the objects are right next to each other like this, or it can mean the objects are right on top of each other, or it can mean the objects are connected by something, connected by a string in this instance, or connected by a string sideways and they're being pulled like that, or they're being pulled upward. But as long as they're connected in any way, so touching really means connected. So if the two objects are connected, these are called two-body diagrams or problems. So we have to draw three free body diagrams in order to solve a two-body problem. The first free body diagram needs to be an individual free body diagram for the first object. Then you're going to draw another free body diagram of the second object. Then you're going to draw a combined one of both objects together. So let me walk you through that. Because objects are touching, we're going to introduce a new type of force, and this is called contact forces. Contact forces are really important. It's the force that an object exerts on another object when they're touching. So here's a box. This box is sitting right next to this box. They are touching, and they are exerting forces. Okay, the green box is experiencing a force on the blue box by pushing against it. So we'll draw the force arrow on the blue box going outward, and we'll label it FC. Okay, the green is pushing on the blue, so we always draw the arrow outward from the box like that. The blue box is going to be pushing back on the green box. So we draw the arrow from the green box going this direction and label it FC. Contact forces, it's kind of interesting, they are the same value. So the contact force felt on the first object, on the blue object, is the same value as the contact force felt on the green object. FC this direction is equal to FC the other direction. The only difference is sign. So FC1, let's say this is the first object, it's negative because it's going in the leftward direction. It's equal to the same as the contact force of your second object. Okay, it's the same number, just different signs. So let's talk about how we see this in the real world. We see this shoe is on the skateboard right here. And when the shoe pushes down on the skateboard, let me use a different color. When the shoe pushes down on the skateboard pushes back on the shoe. Okay? Now, and it's the same force. So the shoe pushing on the skateboard, let's say it's pushing on it with 5 newtons downward. The skateboard actually pushes back on the shoe with 5 newtons forward. Okay? These forces are the same exact value. When the shoe pushes back and the skateboard pushes forward, it actually causes the skateboard to move. This is what is called Newton's third law. So let me come down here and show you our definition. It means every action has an equal and opposite reaction. That's what we're talking about here. The contact force in one direction, it's equal to the contact force in the other direction, like right here. When you're pushing the finger on the wall, that's the contact force of your finger, okay? It's going here in the negative direction. Why is the wall not moving? Because the wall pushes back with the same exact value, okay? And they equal each other. This is why birds can fly. So I'm going to show you this picture here. This bird loves Newton's third law. And I kind of typed it up for you. A bird flies by using its wings. The wings of a bird pushes the air down. So here's the wings, pushes a contact force on the air, okay? And the air, believe it or not, has a contact force that pushes back up on the bird. And so when the air is pushing back up on the bird, it helps the bird to stay afloat. So for every action, there's an equal and opposite reaction. These are called action-reaction force pairs, okay? How many action-reaction force pairs are there in here? Well, the toe is pushing on the football, and the football is pushing back on the toe. In this example, this toe is pushing on the football, and the football's pushing back against the toe. So these are called action-reaction force pairs. They're examples of every action has an equal and opposite reaction. So here's an example of a problem that we're going to solve. And remember, the first thing we do is we draw the free body diagram of our problem. So let me zoom out here. Okay. First, let's look at this problem. It says a 5 kilogram and a 10 kilogram box are touching. So here's just kind of a picture. Here's the 5 kilogram box and the 10 kilogram box, and they're touching. And then it says a 45 Newton horizontal force is applied to the 5 kilogram box in order to accelerate both boxes across the floor. The coefficient of friction is 0.200. Determine acceleration and the contact force. The first thing we do is we draw the individual free body diagrams, okay? Here's your first, and here's your second. I'm going to walk you through how I drew it. Here's the first box. It's sitting on, I'm going to use black. It's sitting on the floor, so you know there's gravity right here, and you know there's normal force right here, okay? Let's pretend right now that we don't have these values, okay? I don't really want you to be given any values right now because we're going to calculate all of these. So we're not given any of these values. So the normal force goes up, the gravity force goes down, okay? We know that this box was pushed because, do you see here? This is the hand. The push is on the blue box. The hand is not touching the yellow box, so there's no applied force on the yellow box. So there's only an applied force on the blue box, so I write applied force right here. This I actually know because the problem tells me. A 45 Newton force is applied to the 5 kilogram box. Okay, so I do know that. Then, if we're pushing the box in this direction, what is slowing it down? Friction is slowing it down, so I drew an arrow this way, labeled it friction. But there's also a contact force because since these are touching, the blue box pushes on the yellow box this way. The yellow box pushes on the blue box this way. Okay, so I took this arrow from the yellow box pushing on the blue box and I put it right here. Okay, because it's going to the left because it's the yellow box is right here and it's pushing on the left of the box. So if anything's touching, you need to draw an arrow going away from the thing that it's touching and label it force, the contact force. Let me say that again. If it's touching anything, you need to draw an arrow away from wherever it's touching that object, okay? This might be interesting. We've never seen two forces on this side. All this means is that the friction force and the contact force added together are both going this direction, okay? Now, underneath this individual diagram, I need you to write down the net force. The net force on this object is not going to be the same as the net force on your other object, okay? Write down the acceleration, the mass, and the coefficient of friction. We know the mass, it's 5 kilograms, and the coefficient of friction is actually given to us in the problem. It's 0.200. So all I'm doing is I'm labeling everything I know, okay? I don't know anything else, so I'm going to leave everything else blank, and I'm going to move over here. Here's the yellow box. We know it has normal force right here. We know it has gravity force down here. It's moving in this direction, right? It's moving over here. That means the friction is going the opposite direction. And the contact force. Remember, you draw the arrow for the contact force opposite the direction of the thing it's touching. So the blue box is supposed to be over here to the left. So the contact force goes over here. There's no applied force on this diagram because you're not applying a force to the yellow box. You're only applying the force to the blue box. So now let's label everything else. The net force, we don't know that. Acceleration, we don't know that. Mass, we do. It's 10 kilograms because the problem told us that. The coefficient of friction will be the same for each box. That's really important. Coefficient of friction will not change for each object. So I'm going to write down here things that stay constant. Okay. And then over here, I'm going to write down things that change. Okay, things that are the same in both diagrams. Your contact force is the same value in both pictures. It's just negative in one picture and positive in another. Coefficient of friction is also the same. Things that change. Your mass changes. Your individual forces change. Your net force is different. Also, things that stay constant, your acceleration. If your objects are tied together, their acceleration is the same. So F of C, the coefficient of friction, and acceleration are actually the same values. So acceleration in both of these objects, whenever we find it, it's the same for both objects. Coefficient of friction is also the same in both objects, as well as your contact force. It's the same in both objects. Okay, so now that we've drawn our two individual diagrams, we have to draw our combined diagram. So your combined diagram, I have my little box and my big box. I'm going to act like it's one thing, okay? Together, they have a normal force. Together, they have gravity. Together, friction is going opposite of their movement. And together, they have a push force in this direction, okay? So, things that we know. Oh, I need to put down here. The net force for this diagram is different from the individual net forces. Okay, all the net forces here are different. The acceleration is actually going to be the same value as the rest of these. Okay, acceleration is always the same for the objects individually and the objects together. Acceleration is the same. The combined mass is going to be different. It's 15 kilograms if I add them together. My coefficient of friction is the same. Okay, coefficient of friction is always going to be the same, right there. And, okay, that's all my information. I've drawn my free body diagrams. I've labeled all the givens. And you always need to include net force, mass, mu, and acceleration underneath your free body diagrams, just like I did here. Okay? Now let's look at what it's asking for. It wants to know the acceleration of the objects and the contact force of the objects. Remember, contact force right here and acceleration is going to be the same for all the diagrams. All right? We're going to find acceleration and we want to find our contact force. So let's walk through this. How can I find, let's say, acceleration? Well, I can find acceleration if I do my net force is my mass times my acceleration. Well, the mass is different for each problem, okay? So if you're trying to find your acceleration from both of your objects, you really could use any of these diagrams to figure it out. But if we look at this diagram here, we don't know the contact force. We don't know the friction force. The only force we know here is the applied. And we don't know any of the forces in this diagram, so it'd be hard to find the net force on those, but it's pretty easy to find the net force on a combined picture. For example, the applied force, we already decided was 45 newtons, because the problem gives us that. So next, let's find the normal force and the gravity force of the combined. So the gravity force, if you remember, is the formula mass times gravity. So mass times gravity. So the mass here is 15. The gravity is negative 9.8. So I put that into my calculator. And I get negative 147. Oops, that's not here. Negative 147 is my gravity. And then my normal force is the same number, it's just positive. So I need to find my friction force. I need to find my friction force. Yes, you can hold the baby. Yes, you can hold the baby.
I'm not asking you about the baby, holding the baby.
So the only other thing I need to find my net force is my friction force. So how do I find friction force? Well, friction force is mu times my normal force, right? Well, mu, we already decided, was 0.200. My normal force is 147. Let's put that in the calculator. And that's 29.4. So now that I have all my forces here, I can actually solve for my net force. My up and down forces are equal, so I just need to do my left and right forces, right? So I do 45 minus 29.4. And my net force is 15.6 to the right. Okay, so now I can find acceleration. My net force combined is 15.6. My mass was 15. What's my acceleration? Well, I have to divide them. 15.6 divided by 15, and it gives me 1.04 meters per second squared. That is going to be the same value for the combined right here, for my individual object, and my other individual object. So you should be able to see that I can now find my net force for each of my individual objects because I have acceleration and mass. So I could find my net force for each of the individual objects by doing this. Let's go ahead and do that next. So my net force is mass times acceleration. So mass is 5, acceleration is 1.04. So my net force is 5.2 newtons. 5.2 newtons. What about over here? Well, it's mass times acceleration again. So my mass here is 10. My acceleration is still 1.04. And so my acceleration now is my net force is 10.4 newtons. So now that I have my net force for each of these diagrams, I could find my contact force for each of the diagrams, okay? Let's do this one right here, because it says it wants to know the contact force. That was one of our questions. So our net force is 10.4 newtons. We know our normal force and our gravitational force are canceling each other out, right? So the only thing we have here is our friction and our contact force. So it's our contact force is going forward. So it's our contact force minus our friction force will give us our net force. So we have our net force, it's 10.4. We're looking for our contact force, so we need to find friction force before we can begin. How do I find friction force? Well, friction force is mu, which is 0.200, times the normal force. Well, I guess we need to find the normal force before we can continue. So what's our normal force? Well, it's basically the opposite of our gravitational force, right? How do we find a gravitational force? Well, gravitational force is mass times gravity. So the mass in this is 10, right? This box is 10. Gravity is negative 9.8. So my force of gravity is negative 98 newtons. Let's put that down here. So that means my normal force is the opposite. It's 98 newtons, okay? So let's go ahead and put that in right here. 98 newtons is my normal force. So 98 times 0.2 gives me 19.6. That's my friction force, 19.6. 19.6 is friction. Okay, so now I can find my contact force. My gravity and my normal forces equal each other out. My net force is 10.4. Okay, so I put in 10.4. Oh, I already wrote that. 10.4 equals your contact force minus 19.6. So if I do 10.4 plus 19.6, my contact force is 30 newtons. Okay? What did we say about contact force? It's the same for both sides. So if my contact force is 30 in this direction for the rectangular block, it's negative 30 for this direction. So we could, if we wanted to, find the rest of these forces, but the question's not asking for that. All it wanted was acceleration and contact force. So we're done. Let's try another problem. I want to do a problem down here. I want to do this problem. What I do is draw a diagram of really what's happening here. There's a 7 kilogram box that's attached to a 3 kilogram box by a rope. Here's the 7 kilogram, here's the 3 kilogram. There's a rope, okay? And it's being pulled with a force. There's another rope here being pulled with a force. So that's kind of the basic idea. Let's break down the diagrams. The first object, which is your 7 kilogram box, okay? It's being pulled with a rope, that's a tension force, with 25 newtons. That's what it says right here. It's being pulled with 25 newtons. We know it's sitting on the ground, so friction's going this direction. We also know that it's attached to the box, so there's another force this direction. Okay, it's being attached to this box, so it's got the force of the contact with that rope pulling it this direction. And then we have normal force going up, and then we have gravitational force coming down. Our other box is the 3, so this is the 7 kilogram box. Our next diagram is the 3 kilogram box. This 3 kilogram box, okay, it's got the contact force it's being pulled in this direction, so the contact force is this direction. Friction's the other direction. Here's gravity, and here's the normal force. Okay, and then our combined diagram. Here's our 2 objects right here. Okay, they're being pulled with a tension force of 25 newtons. Gravity's down here. Tension is here. And then normal force is up. Okay, it says determine the acceleration of the boxes. If you want to find the acceleration of the boxes, look at it, find the acceleration in the combined picture versus the individual ones. It's a little bit easier. And then you know the acceleration for the combined boxes is going to equal the acceleration of each individual box. Okay. Coefficient of friction is the same for all objects. So this is the coefficient of friction for all objects because it lists it for us right here. And then their masses are different. This one's 3. This mass is 7. And this mass is 10 because I have to add them together. The net force for this diagram is going to be different from the net force of this diagram and the net force of this diagram. So they all look different, okay? So let's find acceleration over here. How do we find acceleration? We're going to use F equals ma. So we need to find the net force. How do we find the net force? Adding together all of our vectors. So we have this vector already. Let's find the normal and the gravitational force. Gravitational force is by taking our mass times gravity. So negative 98 and positive 98 are our forces here. What's our tension force? Well, tension force is mu times the normal force. So I do 0.120 times my normal force of 98, and my tension force is 11.76. So let's add all these together to find my net force. Well, the top and the bottom ones cancel out. So now I just need to do this force, 25, minus 11.76, which is 13.24. So now I can find acceleration, right? It's F equals ma. So if I rearrange it, it's really the net force divided by mass. So I do 13.24 divided by 10. My acceleration is 1.3. So it's 1.3 for all of them. Remember, it doesn't change for each individual thing. So we found the acceleration. And that's it. So we're done with our problem. We could have asked to find other things, but in this particular problem, all it wanted was acceleration. So we're done. Now you guys can begin your on-your-own problems. Remember, you have to try, you have to attempt them, and I will go over the answers in class. Adios, amigos.